Thanks for the introduction and thanks for having me here in Tokyo at RIKEN. Today I want to talk about two papers I've published in the last 2 to 3 years. And the title of my talk is, as you just said, Towards Efficient Prune Retrain Pipelines. The two papers are the Sparse Model Soups paper and the Parameter Efficient Retraining or PERP paper. So before I start, let me maybe quickly so does this work? Yes. So these are the two papers this talk builds upon. So the sparse model soups paper was published at ICLR last year. The PER paper is currently under review, and both of these papers have been joint work with Christoph Spiegel, who's a postdoc in our group in Berlin, and Sebastian Pokutta, who's my advisor. And I should not forget, even though I didn't put her picture here, Meggy Andoni, who is a former student of mine who also contributed to the PER paper. So, what is this talk all about? Well, so I'm personally, in the last couple of years, most of my research focus was on pruning of neural networks, so making neural networks more efficient. And the setting is basically as follows. So, as I guess most of you know, neural networks are exploding in size. So, we have these scaling laws that basically tell us it still makes sense to scale up the size of neural networks. We see large language models exploding in size, and this trend seems to continue because it still gives us performance benefits. So on this plot on the right, I don't know, can you see my mouse? I hope so. It shows the years on the x-axis and the number of model parameters on the y-axis. And this is on log scale. So here we see a linear relationship. So the number of model parameters actually grows exponentially. And so this graph is kind of outdated already because it ends, as you can see, at 2020 or 2021 or something. But as you know, over the last couple of years, a lot happened. We had this ChatGPT moment, and the models are still being scaled in size. So while we obviously have or obtain great benefits from scaling up these models, this also comes with several drawbacks, which are kind of obvious now, and I think also start to reach the mainstream media. Well, we have efficiency problems, so the training of these large models is slow, the inference is slow. We have storage problems, so with models containing billions of parameters, they are definitely not easily deployable on edge devices such as phones, IoT devices, and the like. And basically, a consequence of the two former problems, we have a cost issue. So there's the study from 2019 which claims that training of an LLM, which is obviously in 2019 was much smaller than what is an LLM now. But training of such an LLM is said to emit as much CO2 as 5 cars in their lifetime. And there's been this estimate of GPT-3 costing around 4.6 million US dollars. I think at the time that was a number that was just an approximation by people because there was no official statement from OpenAI. But according to Wikipedia, Sam Altman himself said that GPT-4 training had cost more than 100 million US dollars. So there is a lot of different approaches to tackle this problem, and one approach, one potential solution, I should say, that I focused on in my PhD is that of pruning. Pruning is basically the removal of parameters from the network. So what do we mean by removal? Well, as you know, these models basically are parameterized by different weight matrices or weight tensors. And when we set a weight to 0, it's the same as removing it because then, of course, it does not contribute to the output anymore. So phrased a bit more mathematically, we want to introduce sparsity into these tensors to reduce storage and compute demands. So the problem we are actually trying to solve here in the most naive formulation, I would say, or the most basic formulation is we're trying to find the weights that minimize a certain loss, that is our training loss, on some training data set. And then this really annoying constraint comes into play. So this L0 norm is technically not a norm, but this constraint just tells us the number of non-zero weights in our parameters should be at least k, where k is some integer. And if you try to solve it like this constraint is basically a combinatorial constraint, and this makes this entire problem intractable. So what people resorted to, or this is one approach people resorted to, is the removal of certain weights of a pre-trained model using certain heuristics. And I think the most common or the most popular heuristic is that of parameter magnitude, where you just remove the weights that are smallest in absolute value. The intuition behind that is basically, well, if a weight is kind of small, then it shouldn't contribute much to the output of this layer, then it shouldn't contribute much to the overall output of the network, so we can probably safely remove it. So in that sketch I draw, there's shown basically three different types of sparsity. That's basically lie because the middle one is not really sparse, so that's just a dense network with all the edges. On the left, we have what is called unstructured sparsity. So these dashed lines are the ones I removed in this example. So unstructured sparsity is basically whenever the zeros in the corresponding tensor matrix appear somewhat unstructured, somewhat random. There is no actual structure we can leverage. As it turns out, well, unstructured pruning or unstructured sparsity is still hard to accelerate on GPUs. It's a bit different on CPUs, but the reason is basically that if you have a lot of zeros that are just randomly scattered around the matrix, then you have a large indexing overhead to actually benefit from that sparsity. So what is even more desirable, even though unstructured sparsity is nice, I guess, is to have structured sparsity where the zeros are in a certain group or in a certain structure. For example, here where I removed all the weights incoming to this neuron, and this is equivalent to just setting this entire row to 0. And this obviously directly gives you performance speedups because you can just drop that row from the matrix. You just reduce the dimension of the matrix by 1, and you basically get the acceleration on the GPU for free, more or less. So that being said, magnitude pruning is one of the most common heuristic. It's really simple to implement. You just have to take the absolute value of your tensor and sort the weights and remove the smallest fraction. And this actually led to an algorithm that is often referred to as IMP, or iterative magnitude pruning. IMP basically does essentially that. So it takes in a pre-trained network, it prunes a fraction of the lowest magnitude weights, and then something interesting happens. As soon as you prune, say, 40% of the weights, most of the time the model will degrade in performance. It will get worse. So what you have to do to recover the performance is to retrain the non-pruned weights for a bit. And why is this called iterative magnitude pruning? Well, you could do this one shot, and for small sparsities, for low sparsities, this might make sense. You can just remove 20% of the network and retrain a bit, and then you're good. But if you're trying to reach higher sparsity levels, then you would like to do that iteratively. So you prune maybe 20% and you retrain a bit. And then you repeat that and prune 20% of the remaining weights and you retrain a bit. And these prune retrain cycles, you iterate them until you reach your desired sparsity. So what's there appears to be a question. I don't know.
Yes, there is a question. The question is, how is the zero norm of the weights upper bounded by sparsity and smaller values usually pruned in practice?
I don't really understand this question. So aren't smaller values usually pruned in practice? So I mean, you mean this constraint? So this basically does not tell you anything yet about how you decide which weights to prune. It just says there should be at the most k weights that are non-pruned. So if you have n weights, then n minus k should be equal to 0. How you select them is not specified by this constraint. Is that what you meant? Okay. Yeah, please go ahead and feel free to ask questions if I'm going too fast. Um, so why shouldn't we use this algorithm? I mean, it's fairly simple. Everyone can implement it, and in practice, it seems to work kind of well. Well, what is said in the literature most of the time is, and this is like one of the cornerstones of my PhD thesis, I would say that this retraining of the non-pruned weights is costly. So, why doesn't this change? No, it changes. Okay, so the problem is basically, or it's an alleged problem of the algorithm that iterative pruning and retraining is costly. So coming back to the title of this talk, efficient prune retrain pipelines, we investigate two different methods that are completely orthogonal to make this pipeline actually more efficient and to somewhat break this narrative that retraining is costly and should be avoided, which is stated in many papers. And just to give you a hint before I properly start, so the first paper I will talk about is the sparse model soups paper, which is basically a way to parallelize the retraining. So say you have 10 epochs of retraining allocated, we can actually parallelize that even though that at the moment seems really counterintuitive. The second one, the prep paper, is about making retraining of LLMs feasible because here for very large models or LLMs, we're in the setting where retraining is not even possible for a single iteration.
Okay, I have a question about
Yeah.
the first one. So
Yeah.
you mean that you have a set of models and to parallelize retraining that for the same goal?
I will come to this in a second. It's basically this was meant as kind of as a hint. I know that it's at this point not really understandable what I mean by this, but it's yeah, we can get back to your question in 15 minutes or something, then I think it will be clear. So yeah, let me start with this paper, sparse model soups. So what's the setup here? Forget sparsity for a moment, please, and let us think about what can we do to leverage multiple models for better performance. So this is a very common task in machine learning, linked to boosting, linked to ensembles. I'll talk about in a second. So the setting is we have M models, theta 1 to theta m. Can we somehow construct a better model theta that uses or leverages this information from the other M models? So the classical approach that actually works really well is that of ensembles, where you average the outputs of these M models. So what you do, you take a sample X, you put it into each of these M models, you get M different outputs, you average the output logits or probability vectors, however, independent of what your actual problem is, and then you basically use this average as your prediction. So, and this is well known to drastically improve generalization performance. This is basically free lunch. This works almost all the time, at least if I oversimplify things a bit. The problem here is, well, if we do that, we need to evaluate M models, right? Sequentially or in parallel, it doesn't matter. You increase the inference time by factor of M. So this is kind of not what we want because this does not address our efficiency issue. A different approach that is, well, better in that regard is parameter averaging, or what people nowadays call model soups. So instead of averaging the outputs of these M models, we actually average the parameters of these M models. So what happens here, so this is just a linear combination of M models. We'll only look at the average for now, so convex combination. And we just create a new model that is given by these averages, by this average. So obviously, this new model is efficient to use. You just have one single architecture you have to evaluate on for one sample. So you don't have the issue that you actually increase the inference time by a factor of M. This does not work as well as ensembles, but it gives you this efficiency benefit, and it comes with, well, a major difficulty. So while ensembles basically work almost all the time, this is not the case for model soups or parameter averaging because these models, they need to reside in a linearly connected loss basin. So think of it this way. Say you have two models they're at different local minima, and the loss along this segment between the two goes something like this. If you now average the two, well, then you end up somewhere in the middle, and the loss can be extremely high. So it is a priori not clear whether you can actually find such models that are linearly connected, are in a linearly connected loss basin. And as it turns out, this is actually hard. Neishabur et al. Showed or empirically showed in 2020 that if you take the same random initialization, split the model up in two, and train the model from scratch with different seeds. So you're starting from the same base model, but using different random seeds. Even then, even when starting from the same random initialization, from the same init, then you can get two models that are in completely different parts of weight space and that are not averageable at all. And well, this is somewhat concerning because, well, how should we find these models then? So, and this is a really nice picture, I think, from lostlandscape.com. It was, I think, based on the work of Garipov et al. This actually shows the loss landscape of a ResNet 20 trained on Cypher 10. So you might ask yourself, this is a very high dimensional model. How can you visualize this in a 2D or 3D or whatever? Well, what they do is actually they take 3 points and they build up the affine plane that is defined by these 3 points, and then they put a grid over this affine plane, and they evaluate a lot of different models that form as affine combinations of these 3 models. In any case, what is interesting about this is that here we have a local minimum, and here, you can see this, but here is another local minimum, and they are actually connected by a very simple curve that is called mode connectivity. However, when we just average the two weights, we end up somewhere here on this bump, and the loss will increase. So this is just to give an intuition why this does not necessarily work to just take two models and average them. So let's get back to sparsity. So we have this problem of weight averaging, and the question we try to answer in this paper is, can we get the benefits of both weight averaging and sparsity and maybe also solve this problem? So for ensembles, I said this is easy. We can get the benefits of, well, output averaging and sparsity really easily. We just obtain multiple sparse models and average the outputs. So we have a lot of efficient models now. We evaluate them all, we average the outputs, and we're good. So this still has the same problem. We have to evaluate M models. They're all efficient maybe, but it's still M. So this kind of negates the approach of sparsity. So the problem is, how do we find models that are both sparse and weight averageable? So ensembles should be kind of as diverse as possible, because if they're all the same, we don't gain any additional information. But what do we do about model soups? Should they be as diverse as possible? Well, if they're completely diverse, I suspect they would be in very different regions in weight space, and you cannot actually average them. So model soup candidates should be kind of diverse enough. You don't want to collapse to a single model because then you have gained nothing, but they shouldn't be too diverse. So how do we address this issue? So in combination with sparsity, there's basically two problems. The first one being, if we average two sparse models, we can actually destroy the sparsity pattern. Consider the small example here just for intuition. We have these two sparse matrices, these two sparse networks on the left and on the right. So the dashed lines are the ones that are pruned in the respective networks. Now you average them. Well, the orange lines are now the ones that had been pruned in one of the two models, but are now not zero anymore, because 0 plus something non-zero is obviously non-zero. So that sparsity has actually decreased. The model is more dense. So this is a problem when we are averaging sparse models. The second problem is the one I talked about. So how do we actually obtain models that are averageable? And the main idea that basically solves them both at the same time goes as follows. So Neishabur et al. Empirically showed if you start from the same random initialization and train with different random seeds, well, you end up in completely different regions of the weight space. So starting from scratch is obviously not not stable enough. And there's also work by Jonathan Frankel et al. That at some point during training, the network becomes stable to the split, meaning if I have a single model randomly initialized, I train it for like 50 epochs or something, and then I create a copy and train both copies with differing random seed, they actually end up in the same loss bezel. So the intuition here is if we are training from the same pre-trained model, this should keep models fairly close. And if we vary the hyperparameters, well, then we should get models that are fairly close, but also diverse, right? So the observation is here, if we take a pre-trained model as IMP does and prune it, then we copy it, say m times, and train these m copies with different hyperparameters, we get averageable models. How does that look like? Forget all the points for a second, just take a look at the blue point. So this is ResNet 50 on ImageNet, pruned to 70% sparsity. Every point here in the scatter plot corresponds to two models, basically. So we prune a single model to 70% sparsity, and we retrain a lot of copies with differing random seed. Now, for every two subset of these retrained models, on the x-axis, we show the best candidate accuracy, which is just the better test accuracy of the two, the higher test accuracy of the two. On the y-axis, we show the super accuracy, which is just the test accuracy after weight averaging these two models. You basically want to be above that 45-degree line because then you get an improvement. And as you can see, just varying the random seed works really well. So this gives us improvements of almost 2% in test accuracy, which is kind of a lot in the test accuracy regime of ImageNet in that height. So what happens here? We have a pre-trained model, we prune it to some sparsity, we copied m times, and we retrain these m copies with different hyperparameters, and we average the resulting model. So this basically is the answer to both of the problems, because first of all, as I showed you in the plot, we get sparse models with superior performance. And secondly, we can average them without destroying the sparsity. Why is that? Recall that we start from the same pruned base model. So we take a pre-trained model, we prune it, and now we copy it. So after copying, you have m models, and they all obviously share the same sparsity pattern because they stem from the same pruned pre-trained model. Now I retrain them. All the zeros are fixed because we retrain only the non-pruned weights, of course, otherwise it would become dense immediately after the first iteration. Well, and then you have m retrained models that you can actually average without increasing the sparsity because they have the zeros at the exact same positions. So the problem is here, if we do IMP in multiple phases, well, we prune a pre-trained model, we retrain m copies, now you would prune each of them again and you would retrain them again. Well, then you can have the situation that the sparsity patterns actually diverge. To avoid this, we basically propose a simple hack, and that is sparse model soups, or what we call SMS, which averages models after each prune retrain cycle to maintain the sparsity. So take a look at the simple sketch. This is our pre-trained model. We prune it. We create m equals 3 copies of it, retrain them, say, with different weight decay or different random seed or whatever. And then instead of continuing to prune and retrain them, we average them and start the process over again with the pruned averaged model. And as such, IMP increases the sparsity. This is the entire algorithm. So does this make any sense? We have to compare to some suitable baselines. So recall, SMS trains m models in parallel for k epochs each. And in a second, we'll get back to your question. So let us talk about 3 simple baselines for now. There's more in the paper, which I omitted here for clarity. So the first baseline we need to beat is obviously IMP, which is the same as SMS with m equals 1. So if we don't beat the base case without averaging, then there's nothing to do. A very hard and a baseline that we would like to beat is what I call IMP m times. This is just an extended IMP formulation. Well, it does not do any averaging, but it increases the retraining duration by a factor of m. So if IMP would normally retrain in one single prune retrain cycle for k epochs, IMP m times would retrain for k times m many epochs. Why do we do this? Well, this method then in total has the same number of retraining epochs per cycle as SMS. So these are completely comparable in that sense. And then we would like to compare to the best candidate baseline, which is just before averaging. Well, or after averaging, we would like to be better than the best averaging candidate. Otherwise, we could just pick the best out of the M models and continue IMP with these. So please don't be overwhelmed by the numbers, but this is a table showing ResNet 50 on ImageNet for a target sparsity of 90% given 3 IMP cycles. So this first column corresponds to the first phase. So we prune to 50-something sparsity. This is the second phase of IMP, 78-something sparsity. And finally, in the third phase, we reach 90% sparsity. These subcolumns show the different values for M, so the number of models that are averageable or that need to be averaged. So let's just focus on M equals 3 for a second. In the first phase, SMS is the accuracy of the network obtained by pruning to 53.6% sparsity, creating M equals 3 copies, retraining them with a different random seed, and averaging them. And as you can see, we clearly improve upon the best candidate. So this is nice already. Averaging makes sense, right? We obviously improve by a lot on classical IMP. So to make things short, the key insight is we outperform all the baselines, and there's more in the paper. At least all the baselines that I think make sense. But coming back to the title of my talk, which is towards efficient prune retrain pipelines, the interesting thing is that SMS actually outperforms this IMP m times. So recall that IMP m times has the same number of retraining epochs per prune retrain cycle than SMS. They both use k times m retraining epochs. And now this addresses your question, I think SMS is fully parallelizable. Because previously, if you did m times k IMP epochs, well, you have to do them sequentially. You cannot do a gradient descent step without knowing the steps before, right? But these M models you train for k epochs each in SMS, you can all train them in parallel. They're completely independent. So if you have enough GPUs, you can train these M models.
So another question is about the storage of the full model. If you set the sparsity at about 50% and set n about equals to 10, I think the storage the storage maybe you need to store the model is comparable to store the full model. I think. Is that correct?
Yeah. I mean, for unstructured sparsity, the story is a bit more difficult because leveraging these storage gains is not that easy. You still have that indexing overhead. But yeah, technically, if you do it properly, then the individual models are smaller, yeah.
So I would like to know if just for the simplest case, maybe the minimal storage in your case set sparsity about 90% and set n equals to 3. So how much? How much about the performance loss about the comparable to the full model it will be? So what's the gap between your point and the retrain model about comparable to the full, maybe the model that retrain in the full model size?
The performance gap, well, so I mean, if we take a look at sparsity equals to 90%, M equals 3, right? So yeah. SMS will achieve something around 74.53.
Yeah. So maybe the skyline of the full model retraining is how much? What's the accuracy about that?
The accuracy of the full model retraining is 73.59. This is IMP.
Oh, yeah. Okay. Yeah, okay, I see.
So this is obviously has a much shorter retraining duration than SMS in total, but that's why I introduced this IMP m times, and this is that's a bit worse. The interesting thing here is, well, so SMS gives you better performance than IMP, even if you do it in an extended fashion. And now you could say, well, okay, that's nice. If I have the same number of retrain epochs for SMS and the same number of retrain epochs for these IMP M times, and they achieve the same performance. Is there something gained? Yes, there definitely is, because you can parallelize. You can, if you have enough hardware resources, then you can just reduce the wall training time. But in addition to this observation, you still have that SMS actually gives you better results. I mean, here on ImageNet, it's not, I mean, there's a consistent improvement, and we did a lot of experiments, but here it's not as drastic. On other data sets, you see more drastic improvements. So,
Yes, okay. Thanks for answering my question.
yeah, thanks for the question. It's a very good point. To conclude, sparse model soups, what was the challenge? Well, we wanted to combine sparsity and model averaging. The main insight was that models retrained with different hyperparameters are averageable. I think this is the key insight of the paper overall. And the results were, well, we get better performance than all the baselines. I just showed you in distribution cases. This is actually true for out of distribution data sets as well. If you take corrupted versions of ImageNet, we actually find that SMS is much more robust than IMP. So the main takeaway here is that SMS creates a single sparse high-performing model in potentially less time than IMP, and this partially addresses the criticism of retraining in IMP being too costly. We can actually show that with this averaging procedure we proposed, we can drop the cost of retraining a bit. So now to something somewhat orthogonal. Now we're in a different setting, in the same but different setting, so to say. Now imagine you're in a situation where you don't really care about, well, I cannot do 10 retraining epochs because it's too costly. You're in a situation where the model is so big that you cannot actually do a single iteration of retraining. Think of a really large LLM. You don't have a million GPUs to train it on. What do you do? So these simple heuristics I introduced, for example, like magnitude pruning, they all require retraining to recover performance. If you remove 70% of a pre-trained model, it will output complete gibberish. It will drop to near random levels, so you need that retraining. But retraining classically involves updating all of the remaining parameters to recover that performance, that pruning-induced performance degradation. And for large language models, well, for LLMs, this full retraining is really demanding. Think of it like this. In terms of memory, a classical optimizer you would use is something like Adam. So Adam needs to store the parameters, the gradients, the first order, the first moment, sorry, so momentum, and the second moment. And then in addition, it needs to store, well, most of the output activations to do backpropagation. So this is just a hand wavy calculation, but you can easily get a factor of 4 to 5 on your original model size just for the optimizer. And if your model is, well, has 100 billion parameters, this is infeasible unless you have a lot of GPUs. So the same holds for compute. Well, even if you have that many GPUs, you don't want to backpropagate through billions of parameters because it's just slow and costly. So the overall narrative that existed in the literature was basically retraining is infeasible for LLMs. You cannot do it. And there's growing interest in retraining free methods. So people propose, you might have heard of Wanda and SparseGPT and so on. They propose certain methods that actually try to avoid retraining entirely because it's infeasible. So the question of this project was, can we make retraining feasible for large language models? And the answer to that is positive. So the hypothesis we had was that retraining all parameters might be unnecessary, right? I said during retraining, you typically retrain all non-pruned parameters. And the hypothesis is retraining a small subset of these parameters, if choosing a very expressive subset, might suffice. The idea is to update these tiny parameter subsets, such as updating only the biases or only the layer normalization parameters. And this is very much linked to what people do for parameter efficient fine-tuning techniques, right? So there you are in a different setting because you kind of have a distribution shift. You have a pre-trained model, and then you want to fine-tune to some task, which might be something completely different. The overall idea I had with this project was, well, if we have this distribution shift for transfer learning, well, we might be able to interpret the pruning, which catapults your model into or teleports your model into a completely different region and weight space with high loss. Maybe we can see this as a sort of distribution shift, and the same techniques might work. So as it turns out, retraining only the biases corresponding to 0.03% of the parameters. This is for some opt LLM by Facebook, or the LN parameters, which corresponds to, well, roughly 0.01% of the parameters. This works surprisingly well, even though pruning severely degrades the model's performance. And this is somewhat surprising because think of it like this: you need to pre-train an LLM. You need a lot of iterations. It takes a long time. You finally reach that loss you hope to achieve. Now you remove 60 or 70% of the parameters, and the model is completely destroyed. You cannot use it. It feels the same like the randomly initialized model. And now by just updating the biases and keeping the rest frozen, you can regain most of that performance. I think that is somewhat surprising. So that is the naive idea, retraining tiny parameter subsets. So on the left, you see on the x-axis, so this is op 2.7b, so 2.7 billion parameters LLM. And on the x-axis, you see the fraction of weights removed, so the sparsity. On the y-axis, you see the test perplexity on a log scale. So perplexity is a measure of performance of language models, and the lower the better. So it's directly opposed to accuracy, where it's the higher the better. So ignore all the lines for now and just take a look at the yellow line. This is no retraining. We just prune and 0% of the parameters are retrained. You see at the high sparsities, the model becomes insanely shit. Full fine-tuning is the direct opposite. You retrain the entire thing. So this is the dark blue curve here. We can see, well, the perplexity starts to increase, but it seems to do fairly well. And now take a look at, for example, biases and LN parameters. So red and pink. So these two curves are fairly close to actually full fine-tuning, even though they correspond to retraining only 0.01% of the total number of parameters. And the observation here is, so we retrain only a tiny parameter subset, and this obviously reduces the memory and compute overhead by a lot. This actually enables retraining of very big models, for example, up 30 billion on a single GPU in minutes. And I have to say, this OP 2.7b is actually the biggest model out of this OP family I was able to fully fine-tune or fully retrain on a single A100 GPU. So going above that in size just doesn't make it possible anymore. What the optimizer needs to store is too big. Obviously, you can offload to CPU, but in that setting where you have everything on the GPU. So the only problem we still have is that, as you can see, for the high sparsities, we actually still have a gap to full fine-tuning. And the remainder of this talk is how do we close this gap? So I guess the most popular PEFT approach that almost everyone knows nowadays is low-rank adaptation, LoRa, which has this very basic idea. Take W in R to the n times m. It's just some matrix out of the transformer. Well, you freeze that matrix, and instead you train two low-rank matrices B and A that are both low rank and have this one dimension being R, and R is much smaller than N and M. So the new forward of this LoRa updated layer, so to say, is instead of performing W times X as you would for some sample X in a normal case, well, you do W plus BA times X, and you actually only update B and A. So this is actually a weird way to write it because you can use the associativity to make this even more efficient. But anyways, so what do you do after having frozen this and trained this in the transfer learning setting? Well, you don't really want to keep these matrices because the inference will be slower if you have to evaluate two matrices, right, for a sample. So after fine-tuning, what you do is you merge W to be W plus BA, and then you just remove B and A and you recover the original architecture, even though with updated weights, and you have never actually updated W. That's nice. So can we just do the same for pruning? Turns out we can't, because B times A will almost all the time be a dense model, or sorry, a dense matrix. And W is the pruned matrix, right? So that is sparse. If we merge B times A as such into W, we actually destroy the sparsity of W, because a dense plus a sparse matrix, or a sparse plus a dense matrix, is dense. And on the other hand, we don't really want to retrain using LoRa and then just keeping B and A and not merging into W, because this then again kind of negates the reason why we introduce sparsity in the first place, because we increase the inference cost if we don't merge these. So among other things, this is one of the solutions we proposed, which we just called mask LoRa. M is the pruning mask of W. So if W is the pruned matrix, then W is equal to M Hadamard product W. So this is the element-wise multiplication. M is just a bit 0, 1 binary mask where 0 corresponds to a weight in W being pruned. So what we do is we either store this matrix or infer it on the fly, which is a bit more costly then. But during the forward pass, we basically compute this then. So recall this was original LoRa, and now we sparsify B times A. And the good thing is this kind of integrates the sparsity into the training. And upon merging, we don't have the problem that we destroy the sparsity. So W is the pruned matrix. And M times Hadamard product BA is a pruned version of BA that has the same sparsity pattern as W, and upon merging, we don't destroy anything. And this simple approach actually works really well. So this is again a lot of numbers, I know. Opt 2.7b, as said, is the largest opt model that I could put on a single GPU, on a single A100, and do full fine-tuning. So you see, so this is the sparsity here. Biases and LN parameters, they perform fairly good, I would say, for the lower sparsities, but collapse in the higher regime. This is what you've already seen in the plot. Well, and if we employ mask LoRa, well, then we do not really match full fine-tuning, but we close much of the gap to full fine-tuning, even though using a bit less than 1% of the parameters during retraining. So
I have a question.
yes.
So you mentioned about that the trainable is 30%, maybe for the second column, the 30% of the parameters is trainable. So how do you, for the full fine-tuning method, how to control which part of the parameter is we fine-tune that?
Yeah, that's a very good question. So if I try to rephrase your question, you're saying if you have 30% sparse matrix, how do you ensure that you only retrain the non-pruned weights? So, I mean, if you have structured sparsity, that would be kind of easy, because then you could just say, let's say the first 3 out of 10 rows are pruned, then you would just use the rows 4 to 10, right? But for unstructured sparsity, you basically have that indexing overhead.
Yeah.
So what you do in practice to make this work is you actually have to keep the pruning mask as a buffer. So in every forward step and backward step, you zero out the weights and in the forward, and you zero out the weights in the gradient in the backward. So this is basically, it's a fake sparsity. It's to do the computation to get the nice numbers, but it doesn't give you any benefit because you have to store the entire matrix the entire time. So we see that Masked-LoRa kind of closes this gap to full fine-tuning, but it still has the issue that we still need to backpropagate a global loss, right? Because we still have the loss at the end, we do a backward on it, and to do that, backpropagation needs all the activations that are stored for the entire model. And even though we're just retraining 1% of the parameters or something, this can be quite large. So an observation here is that many state-of-the-art retraining-free methods like Wanda and SparseGPT, they already operate in a layer-by-layer fashion to avoid using this global loss. And to do so, they use calibration data. So calibration data is basically a small subset of the original data set you try to retrain on, and they prune locally. So they push the calibration data through the first layer, do the operations to prune and maybe reconstruct the remaining weights, and then they go to the next layer. So they don't need to store all the activations. They just go once from the input to the output of the network to do this stuff. So the idea is here they optimize a local layer-wise reconstruction error. So say we're in some transformer layer with weights WL, we have a fixed pruning mask, we have already found that is applied. XL is the input to the layer of the calibration data. So now instead of minimizing the cross entropy or some global loss, what we actually want to find the remaining weights that are the non-prune weights, such that we minimize the L2 norm output distortion on the calibration data. So we want the layer to stay as close as possible in terms of output on this calibration data input. And the problem here is for very, very large models, optimizing just one layer in this full fashion can already be infeasible. So the idea is here, can we apply Masked-LoRa in this layer-wise reconstruction setting? Does this work to replace this by a LoRa product as we have done before? This would be more memory efficient because it requires the activations and gradients for only one layer at a time. And also this can enhance existing retraining-free methods like Wanda and SparseGPT because they have to go through the network anyways with the calibration data. And that works really well. So this is again the zero-shot accuracy using Masked-LoRa reconstruction or not, depending on the X or check mark here, for 50% unstructured sparsity for some opt models. And as you can see, magnitude pruning profits a lot from the reconstruction using Masked-LoRa. This was kind of expected. This is the last model where I could fully fine-tune a single matrix on the GPU without any additional tricks. For Wanda, you can see a nice improvement. For SparseGPT, a bit less of an improvement, which is due to the fact that SparseGPT has already its own reconstruction step basically incorporated in the method. It's not only a pruning method, but also reconstructs the remaining weights. So Masked-LoRa significantly boosts the existing pruning methods. And one thing I found interesting is that it kind of makes simple magnitude pruning somewhat competitive. Because if you compare on fair or equal terms, both Wanda and SparseGPT actually push calibration data through the entire model, and magnitude pruning in its naive version doesn't. So to compare them on fair terms, you could say, well, we should maybe compare reconstruction for magnitude pruning with no reconstruction for Wanda and SparseGPT. And then comparing these numbers, well, for example, here you see this can be actually better than Wanda in that specific setting. Even though I completely acknowledge magnitude pruning is not the method of choice for pruning LLMs, it is known that this does not work that well, which is, I think, due to the outliers in activations of transformer layers that are missed by magnitude pruning. But I think this is an interesting insight nonetheless. So to finally conclude, the challenge of PERP was that full retraining after pruning was considered completely unfeasible or infeasible for large language models. We had the insight basically transferring the idea of PEFT and retraining a tiny fraction of the parameters, for example, the biases, instead of updating the full model. And this turned out to be highly effective and also highly efficient because you update like 0.01% of the total weights. The results were that this works really good, and that mask LoRa was basically the addition to close this gap to full fine-tuning while still preserving the sparsity upon merging. And to bring things even further, this layer-wise approach, this layer-wise reconstruction approach worked as well with mask LoRa, and we were able to improve memory efficiency and also enhance existing pruning methods. So the main takeaway is that PERP makes this retraining of large models like LLMs feasible again. Yes, and this brings me to the end of my talk. Thanks for your attention, and feel free to ask questions.
So, any questions from the audience? You can just speak up or write down in the chat room. So, I think I'm also doing some online ensemble methods, and I use
Ensemble methods,
yes, ensemble methods. We just to handle the efficiency issue, we also use the parameter. We also only because we need to maintain a set of models, so we just update only the linear normalization parameters and the bias in the model updating, and it's also obtained a very comparable results compared to the full fine-tuning methods. And I think for the age of LLMs, we are also considering the efficiency issue. So maybe I think the direction of masking and the sparsity is a very convincing solution to make the fine-tuning methods. It is much more efficient.
Yeah.
To enable the fine-tuning of LLMs.
Yeah.
Yes.
That sounds interesting. Maybe you can also.
Yeah, we can discuss it later. Yeah.
Cool.
Yes. So, okay, so if there is no other questions and it's about the end of the time, so we just end it here. And if you have any other questions, you can just write an email to the speaker today, and you can find all the message, all the details, and also the recorded video in the AIP YouTube channel. Okay, thank you for attending.
Thanks a lot.